Yeah, we have prepared one agenda point only today because we wanted to give a little bit more time for the presentation. This demo was also shown in Rotterdam on the General Assembly, but I found it very, very interesting. And so I asked the colleagues to present that in the call today. And it's about sustainable workload placement and integrated IPCEI-CIS Pilot. And we have all the 4 presenters in, Anja, Jamie, Marco, and Andreas. And with that, I would like to hand over to Andreas first.
Okay. Thank you, Jan. Let's see. Is this full screen now for you?
Yes, it is.
Okay. All right. Thank you, Jan. So this is, as Jan said, this is a joint presentation because we did a joint pilot between SAP, WestfalenWIND IT Systems, and FH Dortmund. The scope of this presentation is that we wanted to show how we can leverage some of the components of each of our initiatives in the IPCEI-CIS project to dynamically determine when and how we can move workload around between different data centers to optimize on sustainability parameters, use cheap green energy if possible, but if not available because there's no wind, etc., move the workload also back to traditional data centers. In this demo that we've done in this pilot, we purely focused on the workload placement, meaning shifting workload between data centers based on recommendations and parameters. We excluded time shifting, which means based on time decide to run workload now or later, which is another optimization problem and another strategy if you want to utilize something like green energy that is not always available, but that one we ignored. So it's pure location placement. And we also did not bother with stateful workloads. So the idea is that we have compute intensive stateless workload. We just want to take the workload, put it somewhere, run it there. If we have to move it, we tear it down, put it somewhere else, run it there, but we did not bother with the typical challenges that you have around data migration, state migration between data centers, and these real world complications that are real challenges but don't necessarily contribute much to the point that we are trying to make here in this demo. The contributions from each of the parties, so from the SAP Apeiro side, we contributed the platform mesh, Kubernetes technology. We use this for the orchestration of the different services involved. We'll see an overview of the architecture in a second. We use this to manage the service lifecycle, and we use this also to run this operator that actually takes recommendations and orchestrates workload placement and movement. From T-Systems and FH Dortmund, both of them contributed a recommender based on different criteria. T-Systems for the focus on sustainability and recommending based on sustainability parameters. FH Dortmund focusing on latency and recommending placement in different data centers based on latency requirements. And both recommenders were connected to the orchestrator, to the operator who put the workload to places. And from WestfalenWIND, we had the green data center servers that run on a wind park. We'll learn more about this in a second, as well as also the energy predictions, wind energy availability predictions that are input to the recommender of the system, which then is input to the operator at the SAP side. The overall landscape looks like this. So we have on the left side here, there we have this picture will build over time, so it'll be easier to understand. On the left side, we have a consumer account on a cloud infrastructure who wants to place workload on data centers and builds up the required infrastructure. In the middle, we have the platform mesh-based workload placement operator logic that actually takes workload from the consumer and puts it on data centers. On the right-hand side, we have two different target clusters, two different data centers that are potential hosts for the workload. And now we'll go into the video showing actually, I'm sorry. And the way how this works is now we focus on the SAP contribution first, and then we go through the different pilots, the contributions from the different companies. The focus now is on the platform mesh side of things, as well as the placement operator logic in this overall diagram. So start rolling the video if I can. Okay, so now let's see how this whole thing builds up step by step. The first thing that we want to do is set up a data center. So we start with having nothing essentially. And now the first step is that the consumer on the left-hand side who has their account in Platform Mesh, they want to set up and enable a data center for workload placement. So in the first step, we now want to set up the data center Frankfurt. So we create a data center resource, the workload placement operator gets this information and enables the Frankfurt resource. All of this is Kubernetes based, so we use custom resource definition files and we apply them into the platform mesh so that the actual changes get then replicated into the environment. So there was now a resource definition file where we say we have a data center in Frankfurt that has GPUs, CPUs, and sits in the European Union. We apply this in our customer account, and now the data center Frankfurt side actually exists. And if we look into the details of this, we again see, okay, now it exists. It has CPUs, GPUs, and sits in the European Union. We also see available resources in this data center. And all of this got replicated now through the platform mesh workload placement operator. And now in the next step, our goal is to take some workload and just get it deployed. In the initial step, oh shit, no, I didn't mean to start this from the beginning, I'm sorry. In the initial step, we'll have no preferences defined, which means it can just be deployed anywhere. And then what should happen is, that this workload comes to the workload placement operator, and the workload placement operator puts it into the data center Frankfurt. Okay, so here again we use Kubernetes custom resource definitions. Here we can see that we define the workload. Down here you can see it's just it's just doing some dummy stuff. That's not the point of what the workload actually does. But we want to deploy it and we place it. The only requirement that we have is that it should run in the European Union, but we don't have any other specific requirements for this workload. Okay, so now we do the same things. We apply the resource in our platform mesh workspace. And if we look at the site workload, we can see that this resource got deployed. And if we query for the details, we can also see that it got deployed into the data center in Frankfurt, which makes sense because it is the only one that we have. We can also, on the other side, go to the data center Frankfurt and check what's going on there. So if you look for the parts in the data center, we can also see that actually here the workload, no preferences, is running in the data center in Frankfurt. Now, we'll go ahead with something that requires green energy. So we want to place the workload that requires green energy, but we'll most likely then use the recommender, and it will go to the Frankfurt data center as well. Okay, so I'll pause this again. So now what is new is we have this workload here that prefers green energy, and we see here for the placement we still have the EU requirement, and we have the green energy preference, which is an optional. We prefer it, but we don't require it. Okay, we'll keep going. Apply this resource as well in our platform mesh workspace as a customer of this cloud infrastructure. Now we have both workloads up and running, both are deployed. If we query for the site for the new workload, obviously also it is running in the data center Frankfurt, and we can also go to the other side and check the workload there. And now we'll see that we have two parts running, the no preferences workload and the prefers green workload is running in Frankfurt as well. Okay, next escalation, now we have workload that requires green energy. We put this to the operator. The operator can use the recommender to get a place recommended, but now there is no suitable target data center available. Okay, so now here we say we require green energy. Running the U, we apply this resource. And now here we can see pause it again. We see we have the other two still running, but for the new one that requires green energy, there's no eligible site available, which means we're kind of stuck. This workload does not run anywhere. So to the rescue, we are now going to set up a new target data center. We create a new site called windpark Münster. The site is then made available also to the workload placement operator, and we register it as a new target, and then we expect that this workload that requires green energy actually has a new home where it can run. Okay. So we'll create this. As expected, we see we have two sites available now, the data center in Frankfurt and the windpark Münster. And by the way, these are real data centers. So these are the telecom systems and the WestfalenWIND data center. And we can now see also that for the new one, it has the capability of green energy. True. And now, as a first step, what we also expect to happen is that we have this workload already running here that prefers green energy, and now we expect this one also to move to the windpark Münster, because we can then fulfill this preference of the workload. And then it will also get removed from the data center in Frankfurt. So if you now check where this workload that prefers green energy is running, it now runs in windpark Münster. So we can see this in the platform mesh from our customer account. And we can see this, pause it again for a bit. Now we can see then here also the decision to move it. Now we have these two data centers available, but the recommender recommended for this workload to run in the windpark Münster data center, and then the placement operator took this recommendation and moved the workload to the windpark Münster site. And also over here now in windpark Münster, we can check for the running available parts, and we'll see that this workload that prefers green energy is now running up there. And what we also expect is that this other workload that requires green energy also has now a suitable target and gets deployed as well based on the recommendation. So this workload did not have an eligible site, and after some reconciliation time, now it is actually also deployed, the required green energy. And if we check for the site where this workload is running, we see that now it's also running in the windpark Münster environment, again based on the recommendations that we have, the available parameters. The only available site for this workload is windpark Münster, and then obviously it runs there. And if we go back on the other side to the data center and check for the available parts, we now also see that we have this required green energy also up and running. And okay, there's some leftover from earlier tests, ignore that, but we have one instance up and running. What we can also now see, okay, so this was what was happening, and this is all real. This was really implemented. You can see how platform mesh used and the operator used this based on Kubernetes and custom resource definition or standard technology in the Kubernetes world. We had workload, we placed it dynamically, and now we move for a second into the Apeiro platform mesh user interface, where we see the representation of the resources in the graphically in the UI. So here we can see the registered sites that are available in the platform mesh. In my platform mesh account as a customer, and I also, if I move to the site workloads, I get a bit of a nicer visual representation of all the workloads that I deployed, the recommendation for this workload from the recommender and the current site where it's actually running. And we can also see there's a schedule running here, so that every couple of minutes, every 10 minutes, there's an evaluation running where the recommender is asked if there's a new, better recommendation for workload, and workload should be moved in this demo. Okay, and this is it. So this ends the SAP part of the presentation. So now we saw the overall setup, the workload, the logic that places workload and recommends, and now we'll drill deeper a bit into the Wind Park Münster Green Energy Data Center. And then what happened there in the IPCEI context. And for that one, Marco, do you want to just take over the screen share yourself so that you can control the video better, or how do you want to do this?
I can. You click and I
can
explain. So
okay.
yeah, so no
okay.
problem. Yeah. Okay, so thanks, Andreas. We are on the upper right-hand side at the wind park, and yeah. So please click to the next slide, please.
It's not. Hang on. Sorry, it's stuck. No.
So
it was too much. Sorry. Here is this one. It's a video. Okay.
It's a video. It starts right now. So as you perhaps know, we're building data centers inside of the pillars of windmills. And here you can see our 3 data centers currently. And if you click on one data center here, you can see on the top right 3 cages with some racks in it. And on the left, upper left, it is in the AF windmill in the wind park. And here you can see the forecast from 10 a.m. to 9 a.m. in 2 days of this exact windmill and the power produced here in kilowatts. So step to this. Right now there is little wind, then wind comes. And here on the down pages, these are the nodes which can be driven with wind energy to that time point, and yellow means from the whole line to the transformer station. And right now we add a 4th data center here in this windmill
I'm sorry, that was
okay.
I wanted to give you a bit of a pause so you can catch up with the video, but then again I messed it up.
No problem. So here we can add a new data center. We choose here this AJ windmill, and on the right-hand side you can enter some properties where it is, and let's say the chillers will have about 40 kilowatts, and it's a 600 kilowatts data center, some tiered capabilities and so on. So a new data center has been born, but it's currently it is empty. And then you can, of course, add some servers to it. Here we add some Intel servers, let's say 200 of those here. And those servers are, of course, resources which consume some energy. Here you can see these servers, some 550 watts. They are max power and idle power.
Michael, your voice is breaking a lot. At least for me, I don't know if it's the same for everyone.
Okay. Oh, sorry. So.
I thought it was only for me, but.
Okay. So where should I continue?
It's just a lot of distortion. I don't know if it's your microphone, maybe.
Okay. I can't.
Maybe it's the connection, the internet. Maybe
yeah, I think it sounds like a robot, so maybe the Bluetooth connection.
Yeah. Or maybe you switch off your camera while you're speaking.
Yeah, that would be a good idea. So perhaps this is better. So here we have the resource. Is it better, or stop
yes,
me
it is.
if it became worse? Okay. So we have here resources, and this is the 200 servers which consume about 550 watts if they are on max power. And
I'll press play again.
so okay, and so we need some customers for those servers. Let's say Antje or Enrico at T-Systems want to use those servers in the new data center, and we make a login for him. Here. Yeah, and then he logs in to this account and adds a new contract. So he wants to hire some of those servers, which we already added to this data center, this new data center. Perhaps from these 200, he wants to have 130 simultaneously with some performance and efficiency class. And here it's important, it's a strict green LA you can choose here to only power those systems if wind is available. So new contract is here. On top of those contracts, workloads can be placed here. And what we do right now is let's add a bigger workload. So have for 8 hours use 110 of those hired nodes at that site, and a second smaller workload for about 2 hours. And then we switch to log in. Oh, okay. On those share of the contract, we give this information via API to T-Systems, how the power is going and how much of those resources can be powered by our own wind energy. And here you can see it in detail. So let's say we plan the bigger one, and as I already said, right now the wind is not blowing, and we plan the smaller one, and the smaller one consumes smaller energy, and so it is placed starting at 11 and not at 12 o'clock here. And below you can see the production of the energy of the windmill. Of the data center and the demand caused by the data center itself, so the chillers and so on, and on top the workload or the energy consumption of the workload in those servers. So it's quite specific, and this information is going based on the contract via API to this recommender of the systems. Okay. That would be my part, I think. So, Andreas, it's possible to hand over to Antje.
Okay, thank you, Marco. Antje, how do you want to do this? Do you want to control the video yourself, or
yeah, maybe that's the easiest way. Okay. You should see the pattern we had before, the architecture. Yes. Is that the right? Okay. Okay, so yeah, my name is Antje Retzer from T-Systems. As already mentioned, we are working on sustainability recommender, which was also used here in this case, and you can see the recommender in the architecture would be here, this box you can see here on the right side of the middle box. And I like to explain the idea of a recommender to compare it to a navigation system you know from your car. So a navigation system would recommend you, for example, the fastest, maybe also the most economic route. And in a similar way, the recommender is here recommending on the most sustainable way in our case. And as Jaime will show later on, can also be a recommender on other aspects as low latency, for example. So what features do we need for this recommendation? So first of all, we want to be cloud native. So we would like to go with a microservices architecture. Then, as mentioned, we are sustainability focused. So we would like to optimize the workload placement on the environmental impact, which can be identified. And of course, like a navigation system as well, we would be as close to real time as possible to know what weather conditions are like, what energy mixes are like, what the current data center availabilities and metrics are like. And also in a further step as a forecast will be in future. And we would then, on basis of this information, have a machine learned powered recommendation on energy price forecasting and workload analysis, because in the end, it's also a matter of price, not only on energy. So what price would be worthwhile to go for greener energy? Then, of course, we would like to have a reliable performance. That's why we need an comprehensive observability on open telemetry based in our case. And we would like to have it GitOps ready for automated deployment and declarative configurations. So what key functionalities did we implement? So first of all, as mentioned, we would like to have placement, Kubernetes placement. So we focused on the clusters on a cluster level to then to have the best application level reliability, but also the optimal performance. Not going on a node level, but if we leave on a Kubernetes cluster level, this is related to the sustainability aspects, and the node level can then go in a later step, which also leads to clear responsibility boundaries. Then we have a dynamic cluster discovery. So we would like to to identify available clusters also in real time and synchronize the related energy data from that clusters. And in the end, for the customer or for the one who's using the recommendation, we need sustainability criteria transparency and scoring, which then leads to the actual recommendation as Andreas has shown. So he said, like, this cluster is green, but what does that mean? So we need a number behind that scoring, which I show later on. Yeah, this is based on an energy price and energy mix data model. And of course, it is accessible via an API. And we need the needed data collection and processing behind for that. So it looks like this, that we have the external data sources on weather, but as well on the available clusters or the available sites where the clusters are situated in. Then we have a regular data collection level, which is collecting the data on a regular basis. And below that, we have the data provider layer, which is then providing the data on demand. So not on a regular basis, but providing on demand if for a workload, which is then here in the machine learning level, is then needed to be recommended where to place it to. And here is where the rubber meets the road, how they say. So here the scoring is done of the available clusters, and also the forecast, if needed, is done here and is then available via API gateway. So how does it look like? So in this example, we have 2 clusters available. We stay here with the example which was already shown. So we have in Paderborn, we have the windmills, and we have in Magdeburg the site from the system side, and we have a scoring here which has a higher scoring for Magdeburg. So we have here as a showcase that the case when a wind is not blowing. And here you can see that besides the score, you will also get additional data like carbon intensity, energy costs, and the like. Then if you have a third cluster available, which we have here for the demo as named as demo 1, then the scoring will adjust accordingly, and you will have then scoring for the 3 clusters, available clusters. Yes, and I can show you how this then would look like on the map. So we have here a scenario where you have a workload with the user. You have a site with wind and a site with solar energy, and you can now see that the sites are connected, and the workload will now be put as wind is blowing to Paderborn in this case, and when wind is not blowing and sun is shining, then it will go to the Magdeburg site, which is solar driven. And yes, that's the idea behind. And I hand over to Jaime for a recommendation on low latency.
Thank you very much, Anthea. Andres, may I share my screen, or do I use yours?
Sure, no, go ahead, and then you can control the video yourself. It's very easier.
Yeah, thanks. So let me see if you can see my screen. Is it available? Okay, great. Then, well, thank you very much, Anthea. I'm Jaime Urbano, part of the Emulate project. And as it was mentioned, we focus in the part of giving a recommendation based on latency, right? One of the focus that we have within our project is within service quality management in an end-to-end way. What do I mean by end-to-end? It means from the device through the network to the federated edge and then to the cloud that we aim to build in this our initiative. And one of these outputs that we have generated, and we are now testing it and demoing it, is this SECAM recommender, which obviously stands for Service Quality Manager Recommender. And just to give you a summary of what you will see, it's our system interacting with platform mesh, because as we have just mentioned, if we think about it, we are planning to deploy the edge, and the concept of edge computing itself is to be closer to the user, right? Why we want to be closer? Well, because mainly we want to ensure that the latency that the user perceives is low. Therefore, let's not say all of the workloads, but the vast majority of the workloads that we will place will definitely have low latency requirements. And there is where we come with our recommender to say, okay, we aim to assess which one of the clusters that you have federated through platform mesh is the best suitable now to allocate your workload. So what we show is exactly that part. And then we try to go a step further, saying once the workload is placed, we want to monitor it, because we need to ensure that if something happens within the cluster, we are able to trigger what I would call a replacement alarm. A replacement alarm means, okay, your service quality metric has gone wrong, right? It's going bad, in this case, latency, right? So you need to recall platform mesh to perform a different placement in the most suitable cluster in order to maintain the service quality. So let me just see if I can get started with the video. Perfect. So we will come here with a use case, which is actually in the automotive domain because of the critical latency requirements there. In concrete, this is basically a car which is streaming the video from its camera to the edge server. And what we plan to do now is to place the server part of this use case, right? So the inference part, which is compute intensive and obviously requires low latency. So initially we have three clusters which have been already federated through platform mesh, one in Berlin, another one in Münster, and a different one in Paderborn. Due to data locality concerns, right, the platform should just place within North Rhine-Westphalia region, which basically contemplates just Münster and Paderborn clusters. So our second recommender uses different inputs. I will summarize them into a distributed collector and performance benchmarking, which basically means that we are continuously collecting metrics and performance of the cluster via really active compute proofs that we deploy within the clusters to assess which one is the best cluster to allocate the workload. So here we see the two clusters, right? We have our systems running there. They are Kuberneteized and ready to be deployed within the federated edge. And initially, we will notice that the Paderborn cluster has been selected. Similarly to what Antje has said before, right? We provide a score where basically the higher score, the better. And this score, let me just pause, will be defined based on all the metrics, historical value, and the active proofs that we are deploying there to understand where you should place the workload. So this is accessible via an API, as you can just see here now. We have a Paderborn cluster, which has a confidence score of 0.26 approximately, and the other one 0.24. They are now extremely near to each other because, as we saw at the very beginning, both clusters are almost empty, right? So the workload will perform equally good and in any of them at this stage. Perfect. It just go back. Let me move. Okay, right. So in here, what we have seen is that the Münster cluster has been scored with 0.24, while the Paderborn cluster, we will see the score is slightly better. And we have currently just the pods that constitute our system. But all of a sudden, from 5, they went to 7. That means that the platform mesh has already performed the workload placement. And we can see here in the clusters that the pods that correspond to our workload has been successfully placed. And now we are indeed connecting a customer or a client to that server just to see how it works, right? So we are just having a car which is driving through Düsseldorf, right? And we can see that the application is properly working. On the top right, you will see the latency, the green line. It is relatively stable. And the other two frames are showing, let me just go back, then it's clear. The other two frames are showing the load that you have in each one of the clusters. So here on the top, just to keep it clear, because we will come back to this figure several times, on the top green line is the latency of the application, and the other two represent the load that is running in each one of the clusters that have been pre-selected and scored by our recommender. And here, obviously, we can see that the application is running. The car, as I said, is streaming the video actually to the cluster. This is really deployed there, right? So the pods are there. The client is really connecting to the cluster and sending the video, and the inference is performed into the cluster. So As we can see, it is working, right? But what we say here is, okay, in the Edge Federation, we need to understand that this thing will be a sharing infrastructure with multiple tenants and constrained resources. So what we said here is, okay, what happens when we start placing different workload and orchestrating this workload? At some point, this will affect the performance of our latency sensitive application. And this is what we are emulating now. We are triggering different workload or pods within the cluster just to show this effect and how we should mitigate this into the continuum. So we have put load, we can see it here, right? The load in the path of our cluster has gone extremely high, and this provides an immediate effect on the end-to-end latency that our client is perceiving. Well, in a safety critical application, this cannot be acceptable, right? This will literally make a huge difference. Therefore, we need to react to these sort of conditions, right? So what we do here is, as we are monitoring how the workload is performing, we can see here the stress pods, right? And we can see that the latency has gone high. So our system is able to identify this situation and say, okay, something is not going correct here, right? So we need to trigger what we call the alarm, right? Here we can see, okay, the pattern cluster is not suitable anymore. The score has really gone down, and the Munster cluster now has a much higher score. This information is fetched to the platform mesh in order to perform the replacement. From 13 pods, now we go to 15 pods, which means that we have placed again the workload there. Remember, it was a stateless workload, right? And now we can see that this workload is effectively running in the new cluster, as you will just see here on the bottom of the screen. What this means that despite the load being high still in the Paderborn cluster, we have now stabilized again the latency, the green line over here, into a good service quality measurement. And we have dynamically migrated this workload based on a different criteria. As we have shown here, and also Antia mentioned it, well, this is latency focus, but you can obviously, I'm pretty sure you have already thought of many use cases where you start stacking these kind of recommendations, right? So you may have something that requires latency, but also green energy, and then you call different recommenders to generate a single score that will give you the most optimal allocation for a certain workload. So this is more or less what we had to show on our part within the contribution. I'm also open to any questions if there is any.
Yeah, thanks all for the nice demos from everybody. So do we have questions in the round? Not all together, please. No question. That means you made a very good job, right? So you explained it very well. Yeah, exactly.
Oh, about I put an icebreaker question maybe.
Yes, Antje, go ahead.
I put a question to Jaime because I was wondering every time you show this this car drive, is that in Bonn or is that somewhere else?
Yeah, it's in Cologne actually. It's a video that we got there, and yeah, it's real Germany shown there.
Okay, because it looks familiar to me, and I was always wondering.
Yeah. Then in fact, maybe it's some of the roads you may have known.
Hey, I have a question. This is Vasu. Hi, all. I think this goes to Jamie. Yeah. So I think on the workload placement, it's nice everyone uses the cloud native standard Kubernetes. And I think the higher up you go into platform mesh, you're abstracting the workload type of definition. But in the end, when you need to run the workload needs to have concrete, let's say, an opinion what the Kubernetes cluster in the end looks like, right? So how far were you able to abstract that? So can I just plug in another Kubernetes cluster of my choice, maybe on my laptop, and just add it into your workload placement environment, simulate the energy API and whatnot? And would your workload run without any problems? I'm just looking at how can this be extended to any type of windmill farm and whatnot, laptops running on solar?
Okay, let me clarify. Was it for me? Because in the part of federation, I may think that maybe this is more the field of platform mesh, or is it directly related on how we provide the recommendation for platform mesh for different workloads in case we have seen different clusters?
Yeah, I'm not sure. I thought you also take control of the workload itself. So, I mean, the one part is the recommendation. I get that, yeah, and the placement. But in the end, if I give you a cluster that uses that is Kubernetes on the front, but then your workload runs and things are not there that the workload expects, how do you deal with that?
Well, yeah. Let me separate a couple of points. First, here we are basically assuming that there is some federation already, which has happened through platform mesh, right? So if you want to register a new cluster, you should do the steps that Andreas has shown to federate this cluster. And well, another assumption which we are taking is that all the clusters that you have there have already, I will call, the stack that you need to make the workload literally work, right?
Okay.
So in this case, I'm assuming, I will forward to you, Andreas, but I'm assuming that you as a customer, you should take care of setting up your Kubernetes in such a way that the workload can migrate. Our role here is, as for now, just giving the score. And once the workload is placed, we have collection of metrics, in this case, OpenTelemetry metrics, to understand the latency. And based on the latency, we trigger a second alarm. But I will now bounce to you, Andreas.
Okay, thanks, Jaime. But I think, that shows that the two places maybe in the overall architecture where these decisions can be made or supported. One is, we had in this demo some very rudimentary static parameters per data center. Does it support green energy? Does it have GPUs? You could extend on this a bit more. And this information is available to the recommenders to decide where to place workload. But then there's this the dynamic aspects that are not bound to the data center that change. Availability of green energy over time, latency over time, where again the recommender decides to put workload somewhere else. But and I guess you could think about putting additional parameters in there to further narrow it down and help the recommender and the orchestrator to find suitable target Kubernetes clusters. But I don't know. We didn't really think much about that challenge and where to put it best and how to deal with it best once we have all type of workloads and all type of requirements.
That is exactly what I was looking for, because on the recommendation side, I was expecting something like okay, there's a Kubernetes green, Kubernetes yellow, Kubernetes red type of label, but you basically expect homogeneity with respect to the workload. But that's exactly where you can also put in heterogeneity, right? So that's what I was looking for. Okay, explains it. Thank you. But a good first approach. Yeah.
Let me add something in the recommender. Maybe it's more aligned with what you mentioned now. Actually, yeah, in the sense that you said you could have different resources, right? That's why we propose actually running this active benchmarking proof, because you may have a cluster with tons of CPUs, last generation, another cluster which is kind of weak, right? So what we are doing is executing these proofs that actually we execute in the different worker nodes to assess the overall performance of the cluster, and this gives us some sort of view of heterogeneity. And yeah, of course, what we, as Andreas said, what we need to see here is that you cannot fit an extremely high workload in a very weak cluster, right? So prior assessment is also done in order to say, okay, at least these clusters have the minimum requirements, and then we run these benchmarking proofs, which are computing active, to perform the score.
Yeah, it's a perfect example for platform mesh and for multi-provider integration. Yeah.
Any other question? Final chance. 3, 2, 1. Okay. So thanks a lot, all four again. Very, very nice presentation. I will share the recording again in the Voila space. And yeah, if there are proposals that you have, just come back to us. Otherwise, have a good time, have a good week. See you next time. Bye-bye.